So for this part of the class, I strongly suggest grab your notebook since you know we do open notes tests anyways. My goal in this part of the class is to help you understand what equivalent resistance is, so be able to describe it in words. Two, be able to compare and contrast series versus parallel. And three, be able to tackle mixed types of equivalent resistance. If I give you a big crazy circuit like the ones last week, you would break it up into its little parts and then be able to add them back together as a whole at the end. So in your notes, equivalent resistance is the last new topic for this unit, and it's basically how a complex circuit acts as a whole. So I want you to imagine one of those complex circuits from last week, right? All those resistors are going to work together. Because of their resistance and because of how they're arranged, they're going to prevent the flow of electrons. They prevent current, right? We can picture them as one single resistor that's preventing current in a predictable way. And that's what we're going to call equivalent resistance. Equivalent resistance is how a group of resistors behaves together. It's the resistance of a single resistor that represents a group. Now, this will make more sense once you see some pictures of how equivalent resistance works. But I want to point out that it's not really a sum, right? It's not really just add the resistors together because part of this depends on how they're arranged. If they're in series, that causes an increase in resistance. If they're arranged in parallel, that causes a decrease in resistance because of what those two mean. So let's do the easy one first. Big fan of series equivalent resistance. I'm skipping this slide. Big fan of series equivalent resistance. So this is the first new equation to write down. Your series equivalent resistance is equal to the sum of the individual resistances. Now, why that is, um, your series equivalent resistance is increasing, like every time you add a new resistor, it increases. And think of this as like adding more resistors is like adding more obstacles, and it adds more obstacles for current. So when you add more resistors in a series circuit, you increase the resistance, you decrease the current because it's harder for electrons to flow, and decreasing current means there's fewer particles carrying energy to the system. So there will be less power. Now, how to use this equation? Big fan, because it's addition. How to use this equation? Let's say you have a section of a circuit that's in series. I have two 50 ohm resistors, and they act like one 100 ohm resistor. These two 50 ohm resistors have an equivalent resistance, so I would write this as Re equals 50 plus 50. Their equivalent resistance is 100 ohms. Together, they act like a 100 ohm resistor. So if I redrew my circuit, let's say I redrew my 100 ohms, my points A and B, I'd be able to redraw that 50 and 50 section on the outside path. I'd be able to replace the 50 and 50 with one 100 ohm resistor. It's kind of like changing like 4 quarters for a dollar. The 50 and 50 together act like a 100 ohm resistor. So I could replace them in the circuit with one 100 ohm resistor. Their equivalent is 100, right? So along that path, we're getting the total resistance. Because those two share the same path, we would call this series, and we'd apply the series equivalent resistance rule. So I figure let's show you two examples of how to use this equation. Um, Example number one is going to be from our lab the other day. This lab that we did last week. We had a 5 a 10, and a 25 ohm resistor. Because they're in series, that means they're all on the same path as each other. And because they're in series, I would get their equivalent resistance by doing RE equals 5 plus 10 plus 25 to give me 40 ohms total. So if you wanted to, you could then go figure out the rest of the circuit, right? You could be like, all right, I find the current by Ohm's law. Since this is in series, the current that leaves the battery goes through each of these light bulbs. It doesn't meet any junctions, so all the current would be the same. So I could go solve this circuit. I could find the current through the battery is 0.225. And because it's in series, they all have the same current as each other. And I could use that to find the voltage drops. So the only new part of this then is that the equivalent resistance was found by adding up the individual resistors in series. Okay, let's do one more example and then we'll switch to parallel. In this example, what if we knew the total voltage, the total current, and I asked you to find a resistor? Oh boy, I'm asking you to find R3, but hmm. Okay, so first off, I see I have two 4.5-volt batteries. I can tell because it's 9 volts total, and I have two batteries. You see the two long positive terminals? So I have 9 volts total, and that current is the same through everywhere in the circuit. So using Ohm's law, I can determine the equivalent resistance by dividing 9 by 0.075 amps. And if the equivalent resistance adds up to 120, then I know 120 is equal to 20 plus something plus 20 plus 10, and I can find R3. If that looks overwhelming to you, it actually makes a lot more sense when you look at it from a chart. When you look at it from a chart, your 9 volts total provides current, so you can use that to find your equivalent resistance being 120. So I'm dividing my 9 by 0.075 to find the 120. And since they're all in series, I know that these resistances need to add up to 120. So I can subtract to find R3. R3 has to be 50 because 20 plus 20 plus 50 plus 20 plus 10 is equal to 120. Okay, so I'm going to leave the rest of this circuit as just we'll figure it out later because I want to get to the parallel stuff. We know that they have the same current everywhere. And if we want to multiply across the row, we can use that to get the voltage. But let's switch gear to parallel circuits. Now, if you look up parallel equivalent resistance, you're probably going to see this equation on top. But I'm going to rearrange that instead to be easier to solve. Parallel equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over all 3, quantity all to the negative 1. In terms of equations that I've given you, this is a more complicated one. So I'm going to show you how to use this in your calculator. I do strongly suggest for this one, use a graphing calculator or Desmos because those two allow you to see the parentheses where you're putting them. They allow you to show your correct order of operations here. Right? Notice this is to the negative 1 power. It's not subtracting the number 1 at the end. Right? So I'm going to suggest use one of those two methods. I don't suggest using it on the phone just because it doesn't show your order of operations. You can't double check your work and see did you put your negative 1 power in the correct place? So this is an important equation. You should have this in your notes. You have open notes test. Write down this parallel equivalent resistance equation, and then let me show you how to use it. The other day in class, we did this lab where we had a 5, a 10, and a 25 ohm resistor in parallel with each other. So if I wanted to tackle that and use my parallel resistance equation, then I would take my 1 over 5 plus 1 over 10 plus 1 over 25 and put that all to the -1 power. Now, if you want, you can totally do this by hand. If you want to least common denominator this and add them, you would have a least common denominator of 50. Then you could do this as, oh, I don't know, is that 10/50ths, right? You could do 10/50ths plus 5/50ths plus 2/50ths, and then take an inverse, right? But the reason I'm suggesting to do this with a calculator is because sometimes people mess up. And instead of remembering to do this with least common denominator, sometimes people do this and they're like, oh, that's 1/40th. And that's just not true because you can't add these. They don't have the same denominator. Right? So what I suggest instead to get this value is use your graphing calculator. The inverse button on a graphing calculator is on the top left, fourth button down. It's an X with a little -1 sign. Because then in my calculator, I would be doing 5 inverse plus 10 inverse plus 25 inverse. In my graphing calculator, I have really nice, easy to work with parentheses right here. And then at the very last step, inverse button one last time. So 5 inverse plus 10 inverse plus 25 inverse, close parentheses, -1 power, gets me 2.94. Okay, so what is up with that? How can my equivalent, like I have more resistors, how can my resistance be lower than any of my resistors? Well, actually, that kind of makes sense. In parallel, adding more resistors in parallel adds more path. And the more paths you have, the easier it is for flow. Adding more resistors in parallel means that I have less resistance. It's easier to flow. An easier flow means more current. More current means more power. Ultimate power. So when I have more resistors, this leads to less resistance. And if you want to check to see that you've done this right, if you have a parallel section, its equivalent resistance should always be lower than your lowest resistance. 2.9 is lower than 5. So I know that I've done this correctly. In parallel, it's easier to go over than trying to force all the electrons through just a 5 ohm resistor. Think of it as like having more lanes open on a highway. More paths means that each individual path has less traffic. The electrons have less pressure and don't have to push against each other as hard. So let's show you one more and I'll show you what this looks like in Desmos. In Desmos, let's say I did a problem that had, I don't know, a 4, and a 2. I would be doing 1/4 plus 1/4 plus 1/2, all to the inverse power. I do like how this looks in Desmos as well, because it lets you see really quickly if you substitute it incorrectly. All right, so I have 1/4 plus 1/4 plus 1/2 to the -1 power equals 1 ohm. And as a check, my equivalent resistance is smaller than the smallest resistor. So my equivalent resistance is 1, that is smaller than 2. So smaller than the smallest resistance. It's easier to go over parallel than it is to do one individual. When we deal with a combined or complex circuit, what we're going to do is we're going to break it down into small sections and deal with those at a time and then recombine them at the end. Okay, so let's say I have this 4 resistor circuit. What I would do as my steps is first, I would identify a section as either being all in series or all in parallel. I'd probably identify section 3, 4, like these two resistors on the side first, as both being in parallel. Then I'm going to calculate using my parallel equivalent resistance equation, just the resistance of that section. I'm going to replace the 3 and 4 ohm resistors with their equivalent and repeat these steps until the entire circuit can be boiled down to just one resistor. So I'm going to show you these 4 steps, step by step, to solve this equivalent resistance problem. Okay, so for this, first I would identify that section 3, 4 is in parallel. Second, I'm going to calculate the equivalent resistance of that section. So that would be 1/10 plus 1/10, all inverse, to make 5 ohms. And here's what makes it equivalent resistance. Those two 10 ohm resistors act like 5 ohms. It's easier to get through 5 ohms because it has 2 paths open, right? So I'm going to replace resistor 3 and resistor 4 because it acts like one 5 ohm resistor. So one more time, imagine look where resistor 3 and resistor 4 are. I'm going to replace them with one 5 ohm resistor. This notation with the 3, 4 down here means that resistors 3 and 4 together act like 5 ohms. So I call this step the redraw and replace. And while it's not necessary for simple circuits, it is 100% useful for more complicated circuits. I see that I'm not done though. I need to repeat until the entire resistor can be represented by, or the entire circuit can be represented by one resistor. And I still have 3 resistors. So I'm going to redo this, all right? So I see of my remaining resistors that they're connected in series. So I start at the top, identify. These 3 resistors are connected in series. All right, calculate equivalent resistance, step 2. Their equivalent resistance in series is 10 plus 10 plus 5, or 25 ohms. When I replace them in the diagram, this whole system acts like one blue resistor with 25 ohms of equivalent resistance. That's why we call it equivalent resistance, is because these 4 resistors together act like 25 ohms. And this 1, 2, 3, 4 down here says that these 4 resistors are acting together like a single 25 ohm resistor. Notice that because this is a combined equivalent resistance, I don't get a 40. I don't get 10 plus 10 plus 10 plus 10 because it wasn't all in series. And I don't get 2.5 because it's not in all parallel. I'm going to get some number between those because it's a combo. So for series and parallel together, I'm expecting some number in between, some number less than 40. 40 would be if they were all in series, and greater than 2.5, which is what it would have been if they were all in parallel. So one more example, and you're going to try this on your own. I'm going to do the example you actually just did. So this one that you actually just did. You had the red section. You identified the red section was in parallel. We used the parallel resistance equation. So R1 and R2 together act like a single 71.4 ohm resistor. R3 and R4 are in parallel, and together they act like a single 127 ohm resistor. So now I'm going to do the replace and redraw step, step 3. I'm going to replace R1 and R2 with a 71.4 ohm resistor. I'm going to replace R3 and R4 with a single 127 ohm resistor. And I know I'm not done yet because I'm not down to a single resistor, but I'm right there. Together, these two resistors are in series, so I can add up their equivalent resistance. Together, all four resistors act like a single 198.4 ohm resistor. So to calculate equivalent resistance, you identify small sections, calculate the equivalent resistance of that section, redraw and replace it in the circuit, and continue simplifying until you get down to just one resistor. So give homework 7.5 a try. All of the problems in 7.1 are aimed at practicing equivalent resistance, especially in more complicated circuits. Best of luck!